All right, cool. We'll get started then. So I'm here to talk about Ember, an open source malware classifier and dataset. All right, my name's Phil Roth. I'm a data scientist at Endgame, and in grad school they told me to always include a picture of me at the South Pole in all of my talks, so I sometimes do that. In grad school I worked on IceCube, which is a neutrino detector at the South Pole, and it was there that I learned machine learning, and now for the last 5 years I've kind of been applying it to the security industry here at Endgame. None of this would have been possible without my co-author, Hiram. Hiram is awesome. He is also the technical director of data science at Endgame, but mostly he's just awesome. So why Ember? What am I doing here? Well, open data sets push machine learning research forward. Machine learning has achieved great results in the last 10 years in language translation, optical character recognition, detecting or identifying what's in images, the objects that are in there. And there's a lot of good reasons for that. One of them is, hardware has gotten a lot better, data sets have gotten a lot bigger, but I'm saying that one of the main reasons they're getting better is the presence of open source benchmark data sets in all of those fields. So what I'm showing you here is a plot from Ben Hamner, and it's showing 20 different open source data sets, and the number of times each data set is cited in NIPS papers, that's a leading machine learning conference in the field, over time. And so as you can see, these benchmark data sets have always existed in the field, but their use has really taken off in the last 10 years. One example of a benchmark data set in an area other than security is MNIST. And this is 70,000 images of just handwritten digits. And they're split into a 60,000 training set and a 10,000 testing set. So researchers can grab those 60,000 images, train a model that recognizes what digit is being written, and then test that model on the test set. And because all the researchers are using the same images, the same division, then they can compare their performance apples to apples. A leading researcher in the field calls MNIST the new unit test. And what he's kind of saying is that the algorithms have kind of surpassed the MNIST's ability to measure how well that each one is doing, because this data set's kind of smaller, and we're doing really well at optical character recognition now. But even though the algorithms kind of move beyond this data set, it's still useful as kind of a sanity check, kind of like a benchmark test. The algorithm works here, so we know it's at least doing something good. Another open source data set that was on that first plot is CIFAR, and this is again just a bunch of images into a training and a testing set. Here though, those images just have one of 10 different things, 10 different classes. And so, the algorithm is supposed to recognize which class this image belongs to. And then there's a version that has 100 different classes. So, like I said, these are very useful to machine learning researchers in other fields, but there's a problem, and that's that security kind of lacks these data sets. And that's been something I've been saying since I've gotten here to the security industry maybe 5 years ago. So it's not due to any malice on anyone's part. There's a lot of good reasons why it's tough to release these data sets in security, and that's because there's personally identifiable information in them. You don't want to release those kind of things to the public. And even if you try and anonymize these data sets, there's been a lot of examples in the past where clever people can come up with attacks that kind of de-anonymize data sets and kind of expose people to information they didn't think they were giving out to the public. It's also tough to release these because you don't want to communicate vulnerabilities to attackers. So even if a company wanted to spur research forward in detecting network intrusions, they might want to open source all their network traffic, all their infrastructure and everything. But that would just kind of show attackers exactly what they need, where to attack and what their vulnerabilities are. So it would be really tough to release something like that. And lastly, intellectual property. And this is especially important in the area that I'm going to be talking about, which is malware identification, where you want to train on benign programs and malicious programs. It's very tough to release those benign programs because, that's what companies are producing, and that's where they make their money. So despite those challenges, there are still some data sets that exist in security for machine learning engineers to practice on, to use. Mike Sconzo here has a great resource for those that's called secrepo.com. I can't recommend this website highly enough. It's great. It's a kind of just lists out all bunch of different third parties who've released data sets like this in the field of security. And not only that, but he tracks his own logs and then releases those. So not only is it like a resource for other people's data, it also creates open data sets as it exists, which is great. So here, I'm going to go through a couple of the data sets that exist on that site, and kind of, by doing that, show you different areas where machine learning can be applied to the security industry. The first one here is domain generation algorithms. So that's when an algorithm creates large number of domain names that can serve as rendezvous for command and control servers. So you have a piece of malware, and it just generates large numbers of domains in a kind of semi-random and unpredictable way. And the malware author, has that algorithm and is able to know when a domain is going to come up. And then they can register one of those large number of domains, and then each of the pieces of that malware is going to go talk to that one domain and get instructions about what to do next. So you can build detectors for this using machine learning, and you would rely on these data sets. The Alexa Top 1 Million will give you a good set of benign, known, safe domains. And then here, listed there's three more kind of resources for DGA-generated domain names. Especially the last one's really good because Johannes there, he's reversed a bunch of these algorithms, kind of shown what these algorithms do in code, and then generates a couple examples for you to use. So I'd highly recommend that last one. So yeah, another thing you can use machine learning for is kind of network intrusion detection. This is an unsupervised learning problem where it's tough to have labeled data. So you're kind of just looking for anomalous network events, and to me this turns into an alert ordering problem. This one's very difficult. I've seen a lot less like successful applications of machine learning in this area, and it's kind of tempting for people like me who come in from a physics background to be like, oh, I'll just look for outliers. But it gets to be a really difficult problem, and there's a lot of failures over the years. But there are data sets available. They're very old. It's the newer like network traffic data sets don't really exist. So now we get to static classification of malware, and that's what I've been working on the last 3 years, and that's what I'll be talking about here. And this is basically the antivirus problem with machine learning. You have a Windows executable file. Is it safe to run, or is it malicious? And there are data sets available, but they're pretty limited. Drebin here, it's not Windows executable files, it's Android APKs instead. VirusShare is a great resource for researchers, but it only provides malicious malware. The Microsoft Malware Challenge, that happened about 2 or 3 years ago, and what Microsoft did was they released malicious files from 10 different families, and they posted them all on this data science competition website called Kaggle.com. But not only was it like only malicious files, but that the PE headers were stripped from those files. So they weren't real files, and you couldn't use like real world techniques on them. I think what they were going for was kind of like next level things. Like you can use the information from the PE header, but what else can you do to classify these malware families into whatever family they're in? But still, that did spur research forward. There are a lot of papers about that Microsoft Malware Challenge dataset. So now I'm going to talk a little bit about static classification of malware and kind of give a little introduction into machine learning in general, and how you would solve this problem with machine learning. So you have a bunch of benign and malicious samples, and you want to train a model. The first thing you need to do is extract features from all of those samples, and you're going to end up extracting maybe 2,000, 3,000 features or something. But to simplify it, you can think, oh, we're just extracting 2 of them, and then we can just plot them on this graph and look exactly at them. So if those features were like file size and number of imports, then you could place it on a plot and then kind of separate the two, the red dots, the malicious dots, from the blue dots. You want to predict new samples as they come in, and the way you can do that is kind of by drawing a boundary and then seeing which side of the boundary the new sample is on. So you can do that with rules. It's very easy to do that with rules, but you end up getting some of the samples wrong. It doesn't have the best performance. So you can turn to machine learning, or using a statistical model that's going to better describe kind of the boundary between the malicious and the benign. And again, this is happening in two dimensions, but you can imagine a much more complicated boundary in a much higher dimensional space. So I think Hiram and I generated this plot using a support vector machine, which is, its purpose is to build a boundary between the two. But there are many other options. And so how can you decide which one's best? Well, I'd say benchmark datasets are for you. So EMBER stands for Endgame Malware Benchmark for Research. We hope it becomes known as MNIST for malware. And so a caveat, I know, EMBER, I think EMBER's a good name. I chose it because the letters line up and it's great. But I also chose it so I could say this joke over and over again. So I hope you guys don't get tired of it, because I'm not going to. All right, so what is EMBER? EMBER is an open source collection of 1.1 million PE file hashes that were scanned sometime in 2017 by VirusTotal. The dataset includes metadata like the hash. It also includes derived features, a model trained on those features, and there is a GitHub repository that makes it easy to work with all of this data. Importantly, it does not include the files themselves. Like I said earlier, that would if we did include all these benign files, they're not ours. We would be releasing other companies' intellectual property into the wild, and we don't own those programs. We can't do that. But we can release derived features from all of those files. So it's divided into a training and test set. We have a 900,000 training set and a 200,000 testing set. The training set is evenly divided between benign, malicious, and unlabeled samples. And the training set data appears chronologically prior to the test data. And this is kind of important because it kind of reflects the nature of the problem. Malware is always evolving. Benign software is always evolving. It looks different over time. But you need to train a model at some point and release it. So you can train a model on all the data you have at one time. But then your goal with that model is to predict new data that comes along, data that malware samples you haven't seen before, or malware families that you haven't seen before. So you need to train a model at some point and then judge its performance on what comes next. So I should have got that song into my presentation here. So all the training data that we provide labels for is October or earlier in 2017, and this is when the data is first seen, when the malware or the benign files are first seen, and then you can train a model on all that data up till then, and then you can test it on samples that are first seen in November and December. And then we provide the month. That's part of the metadata that we're providing. So it's not the exact day, but by providing the month, we allow you to do chronological cross-validation or quantify model performance degradation over time. So, you train a malware model and it detects malware very well, but then malware kind of continues to evolve to things that you haven't seen before, and your model gets worse and worse at classifying that new malware. So what you can do kind of with this data set is choose an arbitrary cutoff and say, we're going to train on data up till June, and then we're going to say, how well does it classify data in July? And then you can say, how well does it classify data in August, and so on. And you can watch how much worse your model becomes. That's a lot of information about the data there. This is what it looks like actually on disk. We're distributing that bzip2 file. It's 1.6 gigabytes on disk. When you extract it and you go into that directory, there's 7 JSON blob files. And each line is actually a JSON blob. We can look into one of these files here. So the first 3 keys in each of those JSON blobs is kind of the metadata. That's the hash. I've already talked about the month, and then the label, 0 for benign, 1 for malicious, and -1 for unlabeled. And then the next keys in each of these blobs are the features themselves. And there are 8 categories of features. And those 8 categories of features fall into two different categories. One, the first that can be calculated just from the raw bytes. All you need is the file itself, and then you can count how many times each byte occurs and so on. You can also extract strings right from that raw data. But in a bunch of these categories of features, you're going to actually need to parse the PE file format. And so we're using an open source solution to do that called Leaf. It's the library to instrument executable formats. And this Quarks Lab open sourced this library, and we rely on it, and we got to give a big shout out to the Quarks Lab people for doing this. All right. One more note before I kind of go through those feature categories. Feature calculation is a two-step process. This is the code. The details are not important, but I just want to highlight that there's two functions to calculate the features from the file itself. And that first step generates these JSON blobs that we're distributing. That's kind of called the raw features. That's what we've been calling the raw features. Once you have that JSON blob, you need to feed it to the second function, and the output of that function is a feature vector, and that's just a vector of floats. Feature vector, once you have a feature vector, you can feed that into a bunch of different machine learning algorithms. A lot of algorithms accept feature vectors. And the model that we're distributing is a gradient boosted decision tree that certainly accepts feature vectors. So the point is, it's a two-step process. We're kind of releasing features in the middle of that process. And we're doing that so that if you think you have a better solution for vectorizing features, that we're using feature hasher. That's a function that's in the open source library scikit-learn. If you think you have a better solution to doing that, then you can take these JSON blobs, vectorize the features yourself, train a new model, and show that its performance is better than the benchmark model that we're releasing. So we have byte histograms. That's just how many times each byte occurs in a file. We also do a byte entropy histogram calculation. This is kind of a sliding window entropy calculation that benchmarks those entropy calculations back to what bytes occur in that window. But there's many more details in that paper that I show there. There's also section information. So we're looking at the PE header. We're looking at what sections occur. We're looking how big they are, how complicated they are. And we're also distributing what the entry section is. Imports and exports. We're showing what libraries functions are imported from and what the function names. And we're also listing all the exports. String information I mentioned. So we're not distributing all the strings that occur in the file. Because we were a little worried about personally identifiable information or intellectual property, so we didn't want to release all those strings. So we're releasing statistics about those strings. And you can see the number of them, their average length. We're doing a histogram of the characters that occur in all the strings. Those last four keys there, that's kind of, we have regular expressions that match strings that might look like a path or might look like a URL. And so then we're just counting up the number of times those types of things occur in the file and then distributing that count. There's also general information here that's just kind of pulled from the PE header itself, and more specific information that's in the PE header, like what machines these files were compiled on, the compiler version. This is all really small, but the data is open source. You can get it for all the 1.1 million samples. So I talked a little bit about vectorization. I just want to dwell on the fact that it's a necessary step before you train a model, and the code that we're releasing defines how you vectorize these JSON blobs into feature vectors. I downloaded the data onto this computer right here, and the feature vectorization took 20 hours. But it can take like as short as 15 minutes on some servers that we have at Endgame, so it varies. So that's a lot of information about all the features we're distributing. I'm going to talk a little bit here about the model we're distributing as well. We trained a model, a gradient boosted decision tree model, and we used the library LightGBM to train that model. This is kind of a summary of the code that we used to train that model. It's very simple. We made no decisions going into it. It's mostly default parameters. There's one parameter we specified there that we're doing a binary classification. But other than that, it's very, very simple. It's about 23 or 25 trees. 25 decision trees. Don't hold me to that though. But yeah, and then that's distributed along with all the features. And again, yeah, I trained the model on this laptop. It took about 3 hours, and it takes a little bit quicker on other servers. Oh yeah, so once you have a model, We've trained it on the 300,000 benign and 300,000 malicious samples that are in the training set. We ignored the unlabeled samples. And then once you have a model, you can then make a prediction on all the data that's in the test set. And that's a histogram of all the scores there. The red is for the scores from the model on the malicious files, and the blue is for those on the benign. And you can see there's a little overlap, which kind of represents the error. But yeah, the scores range from 0 to 1, 1 for more malicious, 0 for more benign. Once you do make all those predictions on the test set, then you can kind of make, you can say how well you're doing and give some performance data. The way I like to do that is a receiver operator characteristic curve. And there's more information about, what that curve is kind of in the paper we're distributing. But this is once you generate that curve, you can calculate the area under it. The more area under that curve, the better your model is at distinguishing benign from malicious. So those are the numbers there. If you can then pick a threshold, like between 0 and 1, you're going to say, okay, 0.871, any score above that, that's malicious, that can't run on a computer. Anything below that, we say is safe. Once you pick a threshold, then you can say what the false positive rate, what the false negative rate, and so on is. And so those numbers are right there. So, big disclaimer, this Ember model is not malware score. This is a research model. Malware score is better optimized, has better features, performs better, and in my totally biased opinion is the best method for protecting your endpoints against malware. It's great. The Ember model, we're distributing it with code that allows you to make predictions. You could conceivably write up some Python that makes predictions and protects your own machines with this Ember model, but I would not suggest it. It's trained on data through October of last year, and because of the constantly evolving nature, Ember is not going to be better. It's not going to be very good at detecting the latest malware. Code, yeah. So let's talk a little bit more about the code. The repo is right there. With it, you can vectorize the features, you can train the model, you can make predictions on new PE files that come in, so you can calculate the features and then use the model that we're distributing to make a prediction. And then there is a notebook in there that kind of generates all the graphs in this presentation and also in the paper that we're distributing. So it's very reproducible. It has files in there that kind of define the Python environment that I ran everything in, so you can pretty much do everything that I did here. So, now that I've released this, Hiram and I hope certain things happen. We hope researchers pick it up and run with it, and we have a bunch of suggestions for what researchers could do. The benchmark model, like I said, we didn't make many decisions. We didn't optimize many parameters. There's a lot of ways that you can improve the benchmark model. You can use feature selection techniques to throw out some of the features that we provide. You could find better features and extract them from the files themselves. So in that case, if you want to do that, you would need access to the files themselves. We don't provide that, but we do provide the hashes so that maybe research institutions or other companies that have access to VirusTotal might be able to download the files themselves and do their own research. Like I said, you can also optimize the LightGBM model parameters with grid search, or you could do some semi-supervised learning that's incorporating information from unlabeled samples into the training itself. That's actually a technique that the winning team from that Microsoft Malware Challenge used. They took the test set where the labels aren't provided, and they trained, they had their first version of the model, and then they classified everything in the test set where there's no labels, and they got some rough labels. And then if something is benign, if they thought something was benign, they just said it was benign and handed it back into the training set and trained a new model. And then that one kind of performed better on the test data in the end. You can get into trouble doing that with overfitting and everything. But, by providing some unlabeled samples, we hope some people do some semi-supervised techniques like that. So that's all to beat the model that we're distributing. There's more directions you can go in. You can, I mentioned this before, quantify the model performance degradation through time. You can build and compare the performance of featureless neural network-based models instead of gradient-boosted decision trees like we relied on. But again, you would need access to the files themselves, which we don't provide, but we're hoping other bigger entities can do that sort of research. And then lastly, this is kind of like an offensive research. You could look into how can you modify the malicious samples that are in the training set to bypass the Ember model or any other models that are out there, and how best can you do that? That's kind of like an offensive research, but I think it's important for defenders to know about what might be coming so that they can be better prepared for those new techniques. All right, demo time. This is where talks are won and lost. So I'm going to don the hat from a winning team to kind of channel some of their winning ways. So trust the process. All right, here we go. So what I'm going to do is I'm going to download some of the latest benign files or latest malicious files from VirusTotal and then use the Ember model to make a prediction on them and see if it gets it right. I already told you that you shouldn't do this. You shouldn't use the Ember model as a protection, but hopefully it does okay. Okay, I did this search this morning. I just want to refresh it so that it's the very latest stuff. All right. So this is for PE files with that 50 or more AV scanners said is malicious. So I'm going to download the malware directly to my computer because I'm a trained professional and I can do that. These are benign files. So let's get one of those. All right. Oh! Curses. It's looking great, guys. It's great. It's going great. All right, that looks ugly. It was better before. All right, let's see. All right. That's the search I did. And then I sorted by what's, by the very latest thing. Like it was first submitted in the last minute or something. So that's for benign files. No scanner thinks it's malicious. And then, similarly here, 50 or more scanners thinks it's malicious. So those, I'd already downloaded those. Let's go over here. They're right there. Okay. So now here's the data. That's the data set that you can go out and download right now. If you extract it all, it looks like this on disk. That's those JSON files. And this is the Ember model there, that last one. And the cool thing about LightGBM is it exports the model and saves them to disk, and it's actually just text. And so you can look at it. You can inspect it. This is some feature importances. If I go up high enough, you can see the actual trees and the decisions it's making and what features it's making those decisions on. It's kind of cool. So this is the code. I've already checked it out. I've already installed it, so I'm not going to try and do that. But there's scripts in here. One to train the whole model from the beginning to end, and one to classify binaries. This is all showing up. Yeah, all right. All right, so let's point it at the model. Ember model. And then let's point it at the... All right, so it loads the model. I got a score of 0.95 and 0.27. Let's just check that. I guess the web pages look bad, so... oh, here. So the malicious one was 185, and we got 95, and the benign one was 593, and we got that pretty low score. So we did it. Victory, just like the 76ers. All right. All right, so Ember, read the paper. It's available on archive. This is a highlight. Evidently, despite increased model size, so in the paper, to understand the sentence, we have the model, we show its performance. We also trained a convolutional neural net. We kind of took the technique from another researcher who said, this is the best way to do this sort of thing without features. And we compared the performance, and the neural net the performance was a little less. It was not as good. And so we evidently, despite increased model size and computational burden, featureless deep learning models have yet to eclipse the performance of models that leverage domain model via parsed features. And what we're saying by that is that the gradient boosted decision trees, they do better. It's an older technique, but right now they do better in the problem of malware classification. Deep learning is great and has had great results in a lot of different fields. Hiram and I just don't think that those kind of leaps and bounds have made it to malware classification. And we hope that, by releasing this data set that we can kind of bring those great results that deep learning has done in other domains into this domain. And so, bring it on. Download the data, get the code. Thanks a lot. Yeah, I didn't fill the hour. Sorry. So I can take lots of questions. So yes. The question was, how did we decide that threshold of 0.871? So we decided what our target false positive rate was going to be at 0.1%, and then we kind of just scanned through the thresholds until we found exactly where we hit that false positive rate of 0.1%. It is, but you don't want to flood. You don't want to flood with alerts. I mean, false positives really decrease confidence in the user of a model. And if you're going to start flagging on people's, the software that they need to do their jobs, they're really not going to trust your model. And so we aim for very, very low false positive rates. That's kind of where we start. Oh, yeah. Oh, no, yeah. I was just kind of trying to motivate why we do that sort of thing. Yeah. I didn't look at the question is, what are the best features? Can you analyze the decision tree and figure out what features it relied on? And yes, you can do that. No, I haven't done that. I've done some studies with Malware Score about what features are best. Section information, the entry section, that sort of thing really helped out. But no, we do need to dive into that. And I do hope that kind of research is spurred by this, because you can do model inspectability, and you kind of can't, right now we just give a number, and it's not there's no information about why the number is that. Why does this model think this is malware? And we're hoping by releasing an open source model, there'll be more research into that, getting better at explaining the decisions the model makes. Anything?
You test it against malware, for example, with PowerShell, you have a PowerShell malware, you try to maybe test it against a variant that is still essentially the same thing, but maybe with some minor changes?
I mean, we've tested it with latest stuff, the stuff we download from VirusTotal, but nothing PowerShell specific. No, I didn't look into that, and no, I didn't really look into the different families and the performance of this model on different families. But yeah, that would be a good area for further study. No plans to do that. It was a lot of work getting this together, and I need to get back to Malware Score. But I hope researchers look at it, and if in publishing more papers about it, a problem becomes, inescapable or something, then maybe we can do a 2018 version later that makes better decisions. But right now we don't have any plans to update it. What was that? Actually, yes, because the feature generation code is released, if you have access to data or PE files that you are interested in, then you can generate those features and release those features. So that's possible, definitely. Yeah. Okay. All right, thanks a lot. I'll be around if you have any more questions. Thanks.